Okay, so let's get underway. We're extremely grateful to Tarmo for making a break from his wonderful summer house, isolated in the forest, venture back into civilization at great personal risk to his office to present to us his recent work, which he presented only a few weeks ago at LIX on interaction laws of monads and comonads, in particular with applications, as we'll see, to effectful computation. Thanks to everybody for joining us during your summer holidays, either by your own free will or in Tarmo's case by compulsion, because he was invited. So welcome to Owls. Thanks for coming back for those of you who participated before, and welcome to those of you who are new participants. Let's just, I'll tell you a little bit about the seminar series. So we really prioritize personal interaction, and we try to make our seminars as similar as possible to a real physical seminar. So we do this in a number of ways. Firstly, we encourage you to keep your video feed turned on. That way you can flick through the participants and you can see who is participating. It's just like looking over your shoulder at a real seminar, and you might notice somebody, one of your friends, think I'll talk to them later. You don't need to worry about slowing down, overburdening people's bandwidth, because Zoom is very good at prioritizing video streams and so on, so you won't cause any issues, hopefully for yourself or for anybody else if you keep your video on. You don't need to worry about disturbing the proceedings because you'll be forcibly muted throughout. If you do want to ask a question, that's fantastic. We encourage questions at all times throughout the seminar and also at the end of the seminar. To indicate you want to ask a question, please use the raise hand feature, which you can find in the participants menu. You might need to click the ... to see more. You might need to click something to see more options if it's not displayed there immediately on the participants menu. If you click raise hand, then I will most of the time interrupt Tarmo and we'll hear your question, and you can deliver your question in full audio and video. We are recording the seminar, so it's available on YouTube afterwards, but you will only be captured by the recording if you ask a question. So if you don't want to be in the recording, that's fine, just don't ask a question, and you won't be captured. The chat room will shortly be turned off. So you'll be able to send a private message to me. Sorry, my children are shouting at each other in the background. You'll be able to send a private message to me. But other than that, the chat room is turned off, and we encourage you to use the raise hand feature if you want to ask a question. And as I say, we really encourage having discussions during the seminar and also after the seminar, as many of you will be familiar with. We hang around in little groups and we chat to each other. And we talk about all sorts of things, maybe even including the talk we've just listened to. So you're welcome to hang around afterwards for the social element of the seminar. Okay, so without further ado, it's my pleasure to introduce Tarmo, who's going to tell us about interaction laws of monads and comonads. Over to you, Tarmo.
Thank you. Can you hear me all well?
Yes, very well.
Very good. Okay, so this is joint work with Shinya Katsumata and Ezekiel Rivas. I've given this talk once or twice before. The LIX talk was given by Exe. I'll try to do my best. I've failed each time so far, but this time perhaps will go better. So what is my motivation? Here is my slogan for today. Computational effects like using storage or talking to the outside world or non-deterministic choice, they happen in interaction. So really, if you want to run an effectful program, which is a piece of syntax that you abstract into a semantic entity you might want to call a computation, then for it to really go ahead, it needs to interact with some sort of environment. It doesn't work on its own, right? So if you need to read from a memory, the program alone is not enough. So there is going to be a red and the blue part in this talk. The red is the program abstracted into a computation. It needs to interact with an environment, which for us can be just anything. It is some evolution of states of the environment, starting from some initial state, but probably there is some underlying machine that is actually producing this behavior, which we do not need to always see. So keep this in mind. The talk is about three concepts: computation, environment, and then interaction between these. Sometimes I might say a co-computation for an environment. That's also a valid word. So what are some examples of this? So for example, a non-deterministic program needs somebody to cast a die to make a choice, right? So you hire an external agent that makes the choice for you. And then the non-deterministic program actually behaves deterministically as if it were, if all the choices are made for it, and can return us a value, hopefully. So a stateful program, what does it need? It needs some sort of environment that coherently responds to fetch and store commands. By which do I mean what? Well, if you store something and then you want to fetch it, you'd expect to get the same thing back, right? Or if you store something, then you store something else, the later write should count. So that's the game here. What's going to happen in the talk is I'm going to study interaction protocols between computations and environments. So the real emphasis is not so much on computations or on environments, but on the protocol that goes between the two. And it will go in two flavors. So I'll talk about functor-functor interaction laws, why these are functors, we'll come there in a minute. And I'll talk about monad-comonad interaction laws. In a nutshell, functor-functor interaction laws are for unrestricted notions of computation. So maybe you want to talk about computations by a particular program or set of programs. Monad-comonad interaction laws, they are a bit more restricted. So these are for notions of computation that are closed under at least doing nothing or just returning, and sequential composition. So, for example, you could use a monad to capture a notion of effectful computation, and you may be able then to write your programs in a language that at least supports skip and semicolon. So you have the possibility of doing nothing and sequential composition. You might want lots more like iteration, but this is not what we'll talk about today. The outline will be the following. So I'll first play with the definitions. I'll tell you what I define functor-functor and monad-comonad interaction laws to be and why they are what they are, or why the definitions are so. Then I give some examples and also some sort of poorer examples or non-examples, some degeneracy theorems. And then I want to spend some time on investigating the problem of given a notion of computation, what is the corresponding universal of environment, universal notion of environment, such that if I have a computation from that notion, then I can always talk to an environment of the corresponding notion. So in some sense, I'm looking, you know, for a notion of environment that gives me the services that I need. So for programs that do fetch and store, you'd expect that it should be some sort of environment that is able to pay you a memory service, for example. And this can go in both directions. So for a notion of computation, you might be interested in the sort of universal notion of co-computation or environment, but also the other way around. So given a notion of environment, so what is the notion of computation that is universal? So the largest or greatest notion of computation that this type of environments can serve. And then I give some examples of those. So the mathematical notions here would be called the duel for the case of functor, and the monad for another functor or for another comonad. But in the case of given a monad, I want to find a corresponding universal comonad. We need something that is called the Swedish duel in algebra. Then I'll spend maybe only 2 minutes to talk about residual interaction laws. So this is a generalization to counteract in particular these degeneracies that I mentioned here under bullet item 2. But not only, I mean, they also have a bigger purpose. And then finally, we ask the question, this is going to be quite abstract, but is this the highest possible level of abstraction? And in fact, not. So functor-functor and monad-comonad interaction laws are a mathematical notion that makes sense given some base category and then the end of functor category over it, and this is where everything happens. But in general, this is not where you need to start from. You can actually just start from a base category which has, you know, enough properties to be similar to an end-of-functor category. And these things for us will be duoidal categories. These are categories with two types of monoidal structure that interact with each other in a certain way. And that is actually all that is needed in order to state what an object-object interaction law should be, or what a monoid-comonoid interaction law should be, which are then generalizations of functor-functor and monad-comonad interaction laws. Okay, let me give you the definition of what a functor-functor interaction law is, and then some examples immediately. We will work in some category with finite products. Actually, symmetric monoidal will work too, but I won't do this here. But for the purpose of the talk, just think the base category is sets and functions. And all my intuitions will be based on this. And let's not go any further. Then what is a functor-functor interaction law? The story is this. You are given two end-of-functors. One is actually for a notion of computation. The other one is for a notion of environment. And then the interaction protocol is described by a family of maps that is natural. And what does this do? For any x and y, it goes from f of x and g of y to x times y. How should you read this? Think of sets x as possible sets of values that computations can work over. Then f of x are the corresponding sets of computations over these values. Or f of x is the set of computation over a set of values x, I should say. That's the red part. The white, the blue part, all sort of a typical variable y. These are sets of states. And then for a given y, g of y is the set of environments over this particular set of states y. And then what an interaction law does is nothing else than take a computation, take an environment, and run them together in interaction. What you want to get back is a single value, which more or less is the return value of the computation. So the computation runs to the end and delivers a value. And the environment is actually able to run further, but it's just stopped because the computation stopped. And it finishes in some state, or it's actually terminated in some state, which is then the final state. Yeah.
Tarmo, can I ask a quick question? So this notion of functor-functor interaction law is symmetrical between f and g, right?
Yes.
But your legend, computations versus environments, it's not so obvious that they are acted on by a symmetry.
No, that's a very nice observation. And in fact, when we go to monad, comonad, and examples of those, you will see that they're not symmetric. And somehow always the computation plays an active part, and in some sense the environment is the passive guy that sits around there and is, you know, you poke it and then it advances, so to say. But here on this level is not yet visible.
I'm sure it wasn't. Okay, please.
Yeah, but let me give an example so then we get a feel for it. But just follow this legend. So on the left always computation, on the right always environment. Computations act over values, environments they work with states, and we can see these states. So here is one particular notion of computations. F over x is this guy. This is for a notion of computation that first outputs an element of O and then continues as a choice where you first input something from alphabet I and then you return a value depending on what the input was. But in the other branch of non-determinism, you actually output some other token from alphabet O prime, and then you finish with value x. So this is just one particular notion of computation which goes like this. First you do some output, then you make a non-deterministic choice. If you happen to go to the left, then you do some input and continue. If you happen to go to the right, then you do some further output, and you're done. For some people, this might be reminiscent of session types, and this is exactly what it is, kind of. What could be a corresponding notion of co-computation or environment that could service these type of computations? This guy wants to output an O. Maybe one thing that the environment could do would be to listen to this O and then, you know, behave accordingly, make some decision based on it. Actually, here the notion of environment is such that what comes out is exactly a decision. So you decide to go to the left or to the right. Thereby, in interaction, you resolve the non-determinism that the computation has. If the co-computation or environment goes to the left, it actually responds to the input request of the computation and then finishes with some state. But if it chooses to go to the right, it listens to the output, to the second output of the computation, and then depending on the result, it could then return some state. So I almost told you, I introduced these two types, or these two functors, parameterless types, for fixed sets OI and O prime, but I already told you what the interaction was that I had in mind in this case. So interaction goes between a computation, which is a guy like this, so a pair of O, and then a pair for continuations for these possible choices. One is a function f, the other one is a pair of O prime and x, and the co-computation is simply G. What the interaction does is G is applied to O, then you are in the place where you actually get back in left or in right, and then depending on what the arguments are here, then you return something. This is one possible interaction, and in some sense it feels like that it should be the canonical one, and it really is. But of course there are other interactions possible. So for example, it's possible that the interaction behaves like this, that when the computation outputs something for the second time, the co-computation doesn't get to know that thing, but still acts on the first output. That only works when the capital O and capital O prime are the same type. But also the G can be varied. So we could have a completely different G. So G prime here is what? Is the following function space. So it's functions that take a number and then they just produce a pair of an I and a Y. So and the interaction could go as follows. So given a function like this, I just apply to 42 because, well, I need some number to go ahead. 42 is a good number. And then I produce I, and also produce a Y. And then these are provided to the computation. And the computation goes ahead with this, this I and produces a final value, and the state that this produced, I just get. So clearly, this G feels a bit like the universal one. This one feels like a very ad hoc one. So for example, it always chooses the non-determinism by going to the left. But that's a possibility. Okay, monad-comonad interaction laws is exactly the same game, but you want to have a notion of computation that's closed under sequence and doing nothing. And then correspondingly, the comonad must be able to be stopped immediately. You know, but the comonad is stopped, but an element of dy can be stopped. It just means you were able to evolve, but you're actually stopped in the state in which you currently are, which is the current initial state, and this is returned. Or you can be stopped in the middle of sequential computation, and then you still need to go ahead in some way. And the proper conditions of what a monad-comonad interaction law are just two commuting diagrams. So monad-comonad interaction law is like an interaction law between the underlying functors, but there is some agreement required between the unit and co-unit and the multiplication and co-multiplication. So let's look at the case of the unit and co-unit. The story here is, if your computation is trivial, it was just made of a value by doing nothing, then having an environment interact with it is the same as just extract the current state, or the initial state, I should rather say, from the environment and return it immediately, don't do anything. If you've got a computation that is actually a sequence of two computations, an outer and an inner one, then doing an interaction with an environment, so this guy here, is the same as first sort of blowing up the environment, which is I record in every state where I can reach in my environment the whole further behavior from that state. So I get an environment not over states, but an environment over environments of states. And then you'll go in two stages of interaction. So first the outer computation interacts with the outer layer here, and then the inner layer here interacts with the inner layer here. Let me give you some examples here as well, and go a bit faster. So you could imagine T is the reader monad, dy could be the corresponding co-reader comonad, which would be S times Y. But to make the example more interesting, I can also say the two work on slightly different notions of store. So computation works with views of store. The co-computation can work with sort of internal states of the store. And then I need a lookup function that sort of converts a store into a view of it. And how the interaction goes is obvious. Another possible example would be the state monad interacting with a co-state comonad. And again, you don't need to work over exactly the same state set. You could use something called the lens. So if you can go from internal states to views, and given an old internal state and a new view, you can get a new internal state. Then you can define interaction, which goes like this. So for example, also for binary non-determinism, represented as binary leaf trees, you could have the corresponding notion of environment that are essentially streams where states are interleaved with bits, whether you go decide or tell the computation to go to the left or to the right. So W plus W is obviously the same as 2 times W, so it streams over Y times 2. Monad-comonad interaction laws are actually nothing else than monoids in the category of functor-functor interaction laws, and that, for me, actually was the first reason why we introduced the category of functor-functor interaction laws at all, since the monad-comonad interaction laws, in some sense, are the interesting ones. And what makes this to work is then that functor-functor interaction laws, they don't just form a category, but it's a category with a monoidal structure. This monoidal structure is derived from composition, and therefore you can talk about monoid objects in this monoidal category, and these are exactly the monad-comonad interaction laws. So we had some examples. Let me also give you quickly some non-examples. So here are some degeneracy theorems for functor-functor interaction laws. So if your category not only has products, but it also has well-behaved co-products, so then if the notion of computation, which is a functor here, has a nullary operation, by which I simply mean a natural transformation from constant terminal object to F, or it has a binary commutative operation, so from identity times identity to F, agreeing with symmetry. And if in this situation you have the functor F interacting with the functor G, then G has to be boring. It has to be constant 0. So why is this? Well, intuitively, if this fx here could be, for example, 1 plus x, so it's the maybe functor, how on earth are you going to extract from 1 plus x some element of x? If you are on the left, there is no way to do this, right? So, I mean, there is no way to really service errors in this notion of interaction, and this is the sort of intuition for the first, the degeneracy theorem. So constants or nullary operations make interaction laws not very interesting, but binary commutative operations have the same problem. So, so for example, that means that you do not have interesting interaction laws for the finite multiset or finite power set monad in particular. So there are some measures against it, but we skip it for now. Also for monad and comonad interaction laws, here is a degeneracy theorem, which is a bit more involved. It says things go sour, but not as sour, also when you do not just have a functor, but you have a monad, and the monad has a binary associative operation. So it is a natural transformation, identity times identity to T, satisfying this condition for certain L and R, where the idea is you apply the operation twice, but in two different orders. Then basically any interaction law psi that you can have between T and some given comonad D is a bit boring in the sense that if you've got a computation made out of x times x times x, which you have converted into T of x, which you can do with an associative operation, then the interaction law really cannot use the middle guy, because it's the same as actually taking the two extremal guys, applying the binary operation to them, and then interacting. So this is also a form of degeneracy. So in particular, it says for the list monad, when you interact a computation, non-deterministic computation that you want to see as a list, then this interaction can only ever return you the first or the last element of the list, but never the middle ones. Okay, now to the topic of a universal functor interacting with a given functor. It turns out this is easy. So assume now that C is Cartesian closed. Actually, moreover, I want that many n's exist. So for a functor, for any functor G, you can define its dual, G circ, formally like this. The integral sign stands for an end, but the audience that doesn't know about what it means, just think universal quantifier. Sort of, this is a loose intuition. So G circ of x is the set of polymorphic functions that, given any y, you can go from g of y to x times y. And that is the dual, assuming this end exists. And if the ends exist for all functors, and the functors on C, then the dual actually itself is a functor, a contravariant functor from the category event of functors back to the category event of functors. If not all functors are dualizable, if the end doesn't always exist, you can often restrict to some full subcategory of the end of functor that is closed under dualization. Like finite tree functors is a good example. Now, why did I define the dual? The dual is the greatest functor interacting with G. So the following is true. First look here. So to have some interaction law like this, this doesn't quite work. So going from here to here, you can always factor this going first from here to here. So you convert your computation, your F computation into a G circ computation, and then G circ and G canonically interact. Why this works is interaction laws are actually in bijection with natural transformations like this. And this is very easy to see. Just curry, and then all of a sudden you have y only appearing on the right-hand side, which means you can turn the sort of top-level universal quantifier into a universal quantifier over the right-hand side only, if you think logic. And this is the definition of G circ. So, so therefore, interaction laws between F and G are really natural transformations from F to G circ. So it's clear then that any interaction law in this sense, that you have a natural transformation from F to G circ, obviously factors through G circ, using identity here, but if you translate it over using this bijection, you get this factorization here. And since, as Jamie noticed, this notion is symmetric, of course, the functor-functor interaction law between F and G you can also see as a natural transformation from G to F circ, because it doesn't matter which way I curry. So duals are nice in the sense that you can actually calculate them in quite a few cases using some Yoneda yoga. So for example, for constant 1, you get constant 0. For constant 0, you get constant 1. For plus, you get times always. But then, so this one particularly means that circ actually preserves products, because coproducts are products in the opposite of the category event of functors. But things don't work so well for exponent anymore. So the dual of A arrows blank is actually A times blank. That's nice. But if you generalize this, so if it were A arrows GY, then you do not get an isomorphism of G circ X and A times G circ Y, G circ X. You only get the natural transformation in one direction. So on the slide, I've actually written it also for dependent function spaces and dependent products, but it doesn't matter. So this is where things slightly break. The dual of identity is identity. For compositions, things don't work. So you'd expect that the dual of a composition of two functors is the same as the composition of duals, but you only get the natural transformation in one direction. So the official categorical sort of comment here to make is the dual is a lax monoidal functor, but it isn't a strong monoidal functor. And then, of course, by our degeneracy theorem, we know that if I've got some functor with a nullary or a binary commutative operation, then already we know that G circ has to be constant 0. So that's all very nice. Can we do the same thing for a comonad and a monad? So given a comonad, can I find the greatest monad interacting with it? Or given a monad, can I find the greatest comonad interacting with it? And here there is a good news and there is a bad news. The good news is if you've got a comonad D and you just dualize the underlying functor, you will find a canonical monad structure on that dual of the underlying functor. So the dual of a comonad really is a monad. And this is because this dualization functor itself is lax monoidal, so it sends monoids to monoids. In particular, monoids in the opposite category of the category of endofunctors are comonads. And of course, the monoids in the category of endofunctors are monads, so comonads are sent to monads. That's all nice. The not so good news is we cannot play the same game for monads. And the reason is, or was exactly here. So this guy is not a natural isomorphism. So the dual is not oplex monoidal, so it doesn't in general send comonoids to comonoids. So in particular, it doesn't send monads to comonads. So if you take a monad, take its underlying functor, dualize it, what you do get back doesn't generally carry a comonad structure. So what can you do? So this situation actually also happens in algebra. In this situation, you can do the best thing you can do. And this is called either the Swedish duel or the Hopf duel or the finite duel. So we use the word Swedish duel because the adjective finite doesn't make a lot of sense in this context. And Swidler is a bit more neutral, plus it pays homage to Swidler, of course. So let me tell you informally what it is. Informally, it is the best thing we can do, really. I already said this. So given a monad T, we dualize the underlying functor T. We get T circ. Now that doesn't generally carry a comonad structure, but we're looking after the greatest comonad interacting with my monad. So I have to go a bit smaller so that I can find the comonad structure. So I take a smaller functor such that I can find a comonad structure on it, and not just an arbitrary one, but one that actually agrees with the dual of the unit and the dual of the multiplication in a suitable way. But then, of course, there can be many such. So which one is the best among them? It's the greatest one among the smaller ones. So I take the greatest lower bound, right? And this is all what a Residual dual is. So officially then, given a monad, you say the Residual dual is a comonad with these data, T bullet, eta bullet, mu bullet, together with a natural transformation iota, which is kind of the witness that I went for something that was smaller than the dual on the level of functors. And I want to agree on the level of the dual of the unit. So the co-unit is obtained from the dual of the unit. The co-multiplication is obtained from the dual of the multiplication. You would like to take the co-unit to be simply the composition of the dual of unit with the inverse of E. E is invertible, and that's kind of fine, but you fail here. You'd like to take mu bullet to be, sorry, mu circ composed with the inverse of this guy, but this is not invertible. So all you can do is then you look for some T bullet, eta bullet, mu bullet, such that these two diagrams commute. And of course, you look for the universal one. So if there were some other candidate, D epsilon delta, that would pretend to the same role as these two guys, then I need that this D is smaller than T bullet, and also, you know, the corresponding squares agree via unique comonad map between these. I'm really looking for a universal comonad. So this is formally a nice definition to make, but then the question is what are the properties? The Swedish dual is difficult to compute. I'll just give you some examples. So for the non-empty list monad, which is one possible model of finitary non-determinism, finite non-determinism without the option of failure. Non-empty lists are the same as dependent pairs of a list length and then assignment of a value to every position in the list. By our results about the dual, on the level of functors, this sigma just becomes pi, and this function space becomes times, and that's the dual. And that's the dual functor. But this one doesn't carry the structure of a comonad, so it can't be the Swedish dual, and the Swedish dual is something different, where basically here this times corresponds to finding out whether the list was singleton or more than one element. And if it was more than one element, then you also want to decide whether you want to return the first or the last element of the list, but you will not give access to the middle elements of the list at all. Another nice example is the state monad. So like this, you cannot formally use the dual, our formula for the dual, because my formula for the exponent only worked if the codomain of the exponent was a variable, but here it's some functor in a variable. But of course, I can distribute the exponent over times. We get this, and this times can be turned into this arrows here. These arrows can be turned into this times. So formally, the dual of the underlying functor of the state monad is this. But the Swedish dual is what you would expect. It is the co-state comonad. This guy is not. And the interaction here is quite interesting because how does the state monad interaction work? I mean, a computation asks for a state, then the co-state comonad is supposed to provide a state. Then the computation provides a final state, which it informs the environment of. The environment then decides its own internal state based on that, and here a value is returned. That's the normal interaction. But when you interact with the dual of the underlying functor, it's quite different. So the computation asks for an S, and the computation says, I'm not going to give you an S. Tell me what you do with your S. So I have to actually not give an S, but a function from S to S, which I actually have here. This is my planned state transformation. I have to give this information to the environment, and only then it gives me back something. So it really uses a different interaction protocol. Okay, I'm close to the end of my time. I promised to show 2 slides about residual functor-functor interaction laws, which I can do, and 2 slides about abstract interaction laws, which I can do as well, and then I wrap up. Residual interaction laws are just a mechanism to deal with a situation where the environment cannot deal with all of the effect of the computation. Typical examples here are the exception monad or the error monad, maybe monad I mean, because there is nothing the environment can do about it. If the computation doesn't want to yield the value at all, you just cannot make one up, because these interaction laws have to be natural transformations. They have to work for any state set X uniformly, right? And another type of examples that then didn't work were the power set monad and the finite power set, finite multiset. So to counteract these things, you can work with residual interaction laws. The idea is kind of easy. If you cannot deal with an effect, just leave it there. So a residual functor-functor interaction law works with two functors, f and g, and the monad. And then the idea is a computation works together with a co-computation and come back a new computation, a residual computation over values which are pairs of the values of the given computation and states of the environment. So for example, R could be maybe, which just means I refuse to give you any value or any final state. You might ask, why do I need a monad here? But I need it for this category to be monoidal. And if it isn't monoidal, then I cannot find monoid objects in there. And then a residual monad-comonad interaction law is just as before. So there is a monad and a comonad for a notion of computation, for a notion of environment, or for a notion of residual computations or residual effects, and the old conditions, except that you have to, stick in R in suitable places. And then these residual functor-functor interaction laws form a monoidal category, and residual monad-comonad interaction laws are the monoid objects in there. Going a bit more abstract, what are interaction laws really? Look here. Here is yet a different way of looking at what an interaction law is. It's a natural transformation from fx times gy to x times y, natural in x and y. By Yoneda, these are natural transformations from function spaces x times y to z to fx times gy to z, natural in x, y, and z. Now let's uncurry. And then x and y will only occur on the left, and then we can existentially quantify, then we get a Cohen formula for the day convolution. So really, a functor-functor interaction law between f and g is nothing else than a natural transformation from f star g to identity, where star is the day convolution, assuming these things exist again. The Cohen exists, and it's defined not even for particular f and g, but for all pairs f and g. So these things are called Chu spaces. So then we could hope that perhaps monad-comonad interaction laws are monoids in the kind of standard category of Chu spaces, but that's not quite true, because the category of Chu spaces has a monoidal structure, but it's built from star. It's built from day convolution. But here we are after a different monoidal structure built from composition, which is nowhere in the picture in the story of Chu spaces. So Chu spaces kind of give you a different perspective, which is yet another way of saying what the functor-functor interaction law is, but they don't give you a good handle of talking about monad-comonad interaction laws. To do that, one can do one more step forward. One can go one more step forward and see what we really use. We use the end-of-functor category, and we use two monoidal structures on it, on our story. One is day convolution, to just state what an interaction law is. And the other one is with respect to which we want monad and comonad interaction laws to be monoid objects too. So there is two monoidal structures around, day convolution and composition. Categories with two monoidal structures interacting with the same way, in the same way that day convolution and composition monoidal structure interact with are called duoidal categories. I won't introduce the definition here, but it's one where you have two monoidal structures and they interact with each other, most importantly via something called the middle floor interchange law. And here I also need that I'm closed with respect to day convolution, because that allows me to form duals. Then in such a situation, given any monoid with respect to the dot monoidal structure, we can define the dual by just saying it is G lolly star R using the closed structure of star, or the right adjoint of star. This guy is lax monoidal. And then there is a general argument that has been provided, for example, by Hasegawa, but also by Aguiar, which says that in this case, the comma category, F down arrow circ, has a dot-based monoidal structure. And everything we did is actually an instance of this guy, where you take calligraphic F to be the end of functor category. The first monoidal structure is the composition monoidal structure. The other one is the day convolution monoidal structure, which is not just monoidal, but it's symmetric and it's also closed, with a dual with respect to R is the closure functor. And then we get that monad-comonad interaction laws correspond to monoids in this monoidal category. But basically what we've done is, now we've got a notion of object-object functor laws, which are just objects in this comma category, and monoid-comonoid interaction laws, which are monoids in this comma category. I think I should go to my takeaway. So what we have is a single framework for talking about computations, environments, and interaction. There's lots of mathematical structure around. A lot can be stated very generally, and there is also lots of stuff that can be pulled from categorical literature, either in sort of algebra, co-algebra, people around Hans Porscht, for example, and others, and also lots of Australian category theory can be used, having to do with dual categories, for example. So I find this is nice. I find that it's nice that we can talk not only about effectful computations, but the other side of the story, environments in the same picture. We can talk about the closed system, where we put the computation and the environment together to form a closed system. What's there to do? There is lots to do. So there is also something, there are already some things ongoing, which I could mention if somebody asks questions, but just for now. So some of our questions are, what are some good recipes for calculating the Swedish duel? It's clearly much harder than calculating the duel in the general case. We know a few special cases. So in particular, we know what to do when the monad is given by an algebraic theory. Then how to compute the Swedish duel in the residual case when the monad R is present for the residual effect. For this, we have no idea. And then there is, obviously, there must be lots of connections to session types work, not so much for monad-comonad interaction laws, which is not what they are interested in, but functor-functor interaction laws, which we want to find out. And then possibly also similar places in semantics where duals enter the game. So one possible place is game semantics, which we know very little about, but of course there must be connections, and maybe someone can tell me right away what they are. But let me stop here because I already went too long.
Thanks very much, Tarmo. I'm going to unmute everybody so that we can all applaud. Thank Tarmo for that great talk. Okay, so does anybody have any questions? We have a question from David Spivak. Please go ahead, David.
Hi, Tarmo. Great talk. Thanks. Most of the functors you wrote down were polynomial functors. And so comonads and poly, as you proved, are categories. But monoids and poly, at least special ones, are operads. The monads and the comonads are operads and categories. So can you say something about, operads is one object. Can you say something about what comonad interaction law means for an operad and a category?
I can't, but the connection you pointed out is very good. So we could, for example, ask, what happens when I take the dual of a polynomial comonad, and then you really get what we in some papers call the dependent update monad, but it's a form of an operad. So that's one connection.
Do you know whether that particular monad, whether the maps defining the monad, the unit and the multiplication, are Cartesian in the sense that they are isomorphisms?
No, exactly. This one has to be dropped. And there is also in terms of operands, you're also non-symmetric. And there is more to be said, but I don't want to say online right now because I can get it wrong. But if I were to look up, I could say a bit more technically. But let me also mention another thing, which is related to a question Tom Hirschowitz asked us. So he asked, so the dual of functors is self-adjoint, but it's not a reflection or a co-reflection. But we have a feeling that that for monad-comonad interaction laws under specific assumptions, perhaps, and not generally, because we don't see why it should be the case fully generally. It should be the case that if you start from a comonad, you dualize, you take the Swedish dual, you should get back to the isomorphic, to an isomorphic comonad. And that could also be related to your question, I think. But I can't say more here.
Interesting.
Yes.
Okay, do we have a further question? I have a question that's been sent to me by Ivan, which I'm guessing is Ivan de Liberty by chat. I could also read out that question. So the question is about working over a poset and having a functor which is a closure operator. Do you have any idea what the duality would be in that case? And the conjecture is that the dual of a closure operator is an interior operator.
So you work on a poset and you think the dual. I'm hesitant, but it might be the case, perhaps. I don't really have any feel for the dual defined in this way for the category poset at all. It would be nice if it were the case, right? Yes.
Okay, so maybe something to think about later. I had a question. Do you have an abstract characterization of this duality theory, right? So for adjoint functors, we know we could describe them abstractly in terms of unit and a co-unit, satisfying the triangle equations and so on, right? Are these abstract duals in some sense? I mean, are they duals with respect to the convolution product, or right? Is there some sense in which these are abstract categorical duals? Because it seems they have many nice properties.
Yes. Well, why can't I go back? There are certainly duals in this sense, which is one way to construct duals in duoidal categories, which I think satisfy the axioms of dual in some axiomatic settings. But here I also cannot say more, really.
So you mean given the category of endofunctors with its duoidal structure, given by composition and convolution, then you can obtain your notion of dual some abstract universal way in this manner. I'm not sure.
No, I didn't say this. All I said is, if you write down what the dual is on the level of functors, it is just the right adjoint of blank blank tensor R, blank star R. Yes.
So this is
no, that's rubbish. That's rubbish. So, but it's just so define lonely star as the right adjoint to star. So I was wrong about in which order I abstract out arguments, and then the dual is given. You know, you fix the dualizing object R, and the dual is simply defined as G lonely star R.
Okay, so it is this is a universal.
That's yeah.
With respect to closure of this duoidal product.
Exactly. Yes. But then I suppose it satisfies some axioms for dual, which I don't know what they are in some other settings. So Yes, now I must admit that my knowledge stops short
No, thank you
here.
very much.
Yes, yeah.
Answer. And David Spivak has another question. Go ahead, David.
Could you show again the formula for how composition works with duel? On a couple slides previous, you had some sort of formula, but I don't.
Can you repeat your question?
Yeah, you have a duel, and you also have a tensor, a composition monodal product, or just composition. And how did these? Yeah, maybe it was here. Did you say that?
So the duel is lax monodal with respect to composition. Is that what you mean?
That is what I mean.
Yes.
So the dot there is composition, and the
dot here is composition. Yes.
Okay.
With respect to product, it is monoidal. I mean, strong monoidal. So co-products are sent to products. You get an isomorphism. So that's what it is there.
Okay.
But on the level of composition is lax monoidal, and the fact that it isn't oplax monoidal is the source of all the trouble that we have, and why we need these Swedish duels.
Okay. Thanks a lot.
Okay, so if there are no further questions, I'll unmute everybody again, and we can all thank Tarmo a second time.
Thank you.
Okay, so now I'll now stop the recording.